Hi everybody, welcome to Note 6.2. Today we're going to be talking about transformations of reciprocal functions. Now, before we go on, I want to point out that the inverse variation problems that you worked with on 6.1 are also called the reciprocal function. So inverse variation, reciprocal function, they're synonymous, they're one and the same. But we also want to point out that the reciprocal function is a special type of rational equation that we're going to look at on 6.3. So a reciprocal function is just a special rational equation. Okay, let's look at some vocabulary we're going to need to be successful in this lesson. The first vocabulary word we're going to look at is branch. So what exactly is a branch? Well, let's look at a sketch of what a reciprocal function is going to look like. And again, this is just a sketch because my graph is very bad. But anyway, so most of your reciprocal functions are going to have this shape. The red represents the graph. So you'll notice that those are not continuous. So a reciprocal function is what we call a discontinuous graph because I can't draw the whole thing without picking up my pencil. So you'll notice that there are two separate pieces of the reciprocal function. Well, those two separate pieces, those are each called a branch. So we're looking at two branches of the reciprocal function. So a branch is each piece, each curve. Okay, so a function that can be written in the form of p of x over q of x is what we call a rational function. That means we have a polynomial on the top and a polynomial on the bottom. So we have x's in the top and bottom. That's what we refer to as a rational function. Now, our next word is a reciprocal function. A reciprocal function is a function which belongs to a family whose parent function is y equals 1 over x, where x cannot be 0. So the reciprocal function is a type of rational equation. So the way a reciprocal function differs from a rational function is a rational function you have x's in top and bottom. In a reciprocal function, you only have x's in the bottom. The numerator of a reciprocal function is always a constant. So it's, you know, -1, -2, -5, 5, 7, 9, whatever. But a reciprocal function is a type of rational function that only has constants in the numerators and polynomials in the denominator. Okay, a small disclaimer. You don't need to copy this down. This is a special type of rational function. Now this referring to as reciprocal function. So a reciprocal function is a special type of rational function. You can graph it using the rules we're going to learn on day 3. Day 3 we're going to talk about rational functions. Or you can graph it using the rules we're going to learn today. So I'm going to show you how to graph a reciprocal function today. Then on day 3, I'm going to show you how to graph a rational function. Now, you can use the rules for rational functions on reciprocal functions, but you cannot use the rules for reciprocal functions on rational functions, okay? So the rules for graphing a rational, they work for rational functions, which is day 3, but they also work for reciprocal functions. However, reciprocal function rules only work for graphing reciprocal functions, okay? And again, we're going to study more difficult rational expressions next class, and the graphs we talk about next class are going to be equations that cannot be graphed by a simple shift, okay? So this is going to be using, today's lesson is going to be using A, B, H, and K, much like we're used to. Now let's move on and talk about the reciprocal parent function. So we're going to learn everything we can about the parent function, like the table of values, the asymptotes, intercepts, domain and range. And then once we all learn that, then we can shift it over to moving it up, down, left, right, stretching, shrinking, all that stuff. So our parent function for the reciprocal function is y equals 1 over x. So to complete the table of values, I'm going to take the fab 5, and then I am going to plug each value of the fab 5 into the equation to get the corresponding y value. So 1 over negative 2 is negative 1/2. Well, negative 1/2 is really negative 0.5. And then 1 over negative 1 is negative 1. 1 over 0 can't have a 0 in the denominator because it's undefined. So we're going to write undefined. 1 over 1 is 1. 1 over 2 is 1/2, which is 0.5. Now you're probably wondering, why didn't you write negative 1/2 and 1/2? You can. That's perfectly okay. However, when you're moving things up, down, left, right, stretching, shrinking, sometimes if it's a pretty decimal, it's easier to deal with. All right, so there's our parent function table of values. Now let's talk about asymptotes. And you're probably wondering, well, what is an asymptote? An asymptote is a place on your graph where your function is undefined. So for example, we learn right here that when x is 0, my function is undefined. I may not have a value at x equals 0 because my function is undefined. That puts a 0 in the denominator. So we know we're going to have a vertical asymptote at x equals 0 because x may never, ever, ever equal 0 for the parent function. Okay? So that's how I get x is 0. Now, let's talk about the horizontal asymptote at y equals 0. And you're like, why is it y equals 0? Well, let's say I continue my graph on up here. So let's say I go negative 3, negative 4, negative 5. If I plug in negative 3, I get negative 0.33 repeating. If I plug in negative 4, I get negative 0.25. If I plug in negative 5, I get negative 0.2. And it's the same if I go 3, 4, 5, because 1 over 3 is 0.33, 1 over 4 is 0.25, 1 over 5 is 0.2. So you'll notice that as my x goes to negative infinity, my y's are getting closer and closer to 0. And as my x goes to positive infinity, my y's are also getting closer and closer and closer to 0. So they're getting closer to 0 as they go to negative infinity, and they're getting closer to 0 as x goes to positive infinity. So that's why I have a horizontal asymptote at y equals 0. Now, the definition of an asymptote is a place where your function is undefined that your graph will never touch. Now again, it'll get super duper close, like microscopically close, but it will never cross or intersect or touch the vertical and horizontal asymptote. Never, never, never. Okay, like I said, it'll get super duper close, but it's never going to touch it. So let's plot our vertical and horizontal asymptotes. Then let's plot our points. Obviously, we cannot plot 0 as undefined. Can't plot that, but we can plot negative 2, negative 0.5, negative 1, negative 1, 1, 1, and 2, 0.5. Okay, so now that we've got our asymptotes plotted and that we've got our points plotted, now we can connect the dots. Now notice we're going to connect and we're going to get as close as we can to the vertical asymptote and as close as we can to the horizontal asymptote, but we are never going to touch them. So you'll see again that this is a discontinuous graph because I've got two branches that are not connected. And look at how I connect the dots for the points, but then I hug those asymptotes, okay? So we're going to hug those asymptotes. Now, let's talk about domain and range. Let's talk about domain and range. Now, as my domain comes from negative infinity, it's going to go, 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 and then it's going to hit that brick wall at 0. Okay? Then it's going to pick up on the other side of 0, and then it's going to keep going. So we can see that my domain goes from negative infinity to 0, and then it picks back up at 0 and keeps going to infinity. Now, notice that I used a parentheses versus a bracket at 0. Okay, and the reason I did that is because I can't technically touch 0. I can get super duper duper in its face and get really close, but I'll never cross it. So we can't touch 0 on our graph. So that's why we use parentheses instead. All right, so now let's talk about the range, okay? So as we come from negative infinity, I'm going to go up, 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 and then I hit y equals 0. And then I pick up on the other side and keep going up, 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 up to positive infinity. So same situation, negative infinity to 0, 0 to infinity. And again, we put parentheses because we'll never touch 0. It's on our graph, but we'll never touch it. Now, you may be wondering what these U's stand for. And these U's stand for the union. So it's the union of the two domains. So in terms of domain, my first part of my domain comes from negative infinity to 0, and then 0 to infinity. So it's the union of those two domains. Same thing with the range. It's the union of negative infinity to 0, and then 0 to infinity. So it's the union of those two branches for domain and range. All right, so this is everything we know about the parent function. And you're like, well, that's fine and dandy, but what happens if my asymptotes aren't at 0? We're going to talk about that next. All right, let's talk about how we take this parent function and we move it up, down, left, and right. So that's going to be where A, B, H, and K come from. So you'll notice we have A in the numerator, B is in the denominator, times x minus h. So if you have a b value, you're still going to want to factor it out before you do any movement of up, down, left, and right, okay? And then x minus h, it's still opposite day inside those parentheses. So if it says x minus 5, you're really going to go right 5 and add 5. If it says x plus 5, you're really going to go left 5 and subtract 5. So it's still opposite day in that parentheses as far as h goes. And then and then you have plus k. So we want to talk about the specific effect of a, b, h, and k. So A, just like normal, causes a vertical stretch or shrink, or if it's negative, it causes a reflection. Okay, so A is going to be that value that's in the numerator, that constant value. So, and the reason we say absolute value is because we want you to look at just the number itself. Because if it's negative, that causes something else. So just look at the number, don't look at its sign. Okay, so if A is bigger than 1, we call that, as normal, a vertical stretch. If your A is between 0 and 1, that's a vertical shrink. And if A is less than 0, meaning if A is negative, that's going to cause a reflection over the x-axis. Now, B does the same thing, just affects the horizontal movement. So if B is less than 1, again, absolute value bars, because we want you to just look at the value, not if it's positive or negative. So if B is greater than 1, that's going to be a horizontal shrink. If B is between 0 and 1, that's going to be a horizontal stretch. And then if b is less than 0, meaning b is negative, it's going to be a reflection across the y-axis. Now, if inside that parentheses it's x minus h, that means you are going to go to the right h units. If it's x plus h, you're going to go to the left x units. If your equation or function has plus k, you're going to go up k units. If it is minus k, we're going to go down k units. So again, the a, b, h, and k, they haven't really changed. It's just where they're located has changed. All right, given f of x equals a over b times x minus h plus k, does a, b, h, or k cause the asymptotes to move off of the xy axis? Well, let's look at our graph, okay? So here's a graph, and let's talk about our asymptotes. So we have an asymptote here at y equals 0. This is our parent function. Oops. This is our parent function where we have x equals 0. Okay, and here are our branches. So here's the thing. Once you plot the branches and the asymptotes, they move together as one. So if your branches go up 1, your asymptote goes up. If your branches go left 2, then your asymptotes go left 2. So we discovered that it's really the h and k that cause movement off of the axis. Okay, so h and k are the reason we move, our asymptotes move off of those axes. A and B just stretch and shrink, they don't move it. But h moves us left or right and k moves us up or down. So they all go together like they're glued in place together. So if your graph shifts to the left 5, your vertical asymptote shifts to the left 5. If your graph goes up 3, then your asymptotes go up 3 because they move together. Okay? So let's talk about, well, how do we determine what the vertical asymptote is and what the horizontal asymptote is? Well, the vertical asymptote is simple to remember. It is simply x equals h. Okay, simply x equals h. Our horizontal asymptote is y equals k. So the vertical asymptote is x equals h. The horizontal asymptote is y equals k. Let's talk about, well, how does that affect the domain? Because if you remember, the domain is negative infinity to that vertical asymptote union vertical asymptote to positive infinity. Okay, so let's talk about, well, if I know my asymptotes at h, then that means my domain is going to be negative infinity to h union h to infinity. Similarly, the range, remember the range was negative infinity to the horizontal asymptote and then horizontal asymptote to positive infinity. So if my asymptote is at k, then that means my range is negative infinity to k union k to infinity. Okay, so again, remember it's negative infinity to the vertical asymptote union vertical asymptote to infinity, and then for the range, it's negative infinity to the horizontal asymptote union horizontal asymptote to infinity. Okay, so negative infinity to k union k to infinity. Now, if you forget that, just remember again that it's negative infinity to the horizontal asymptote to infinity every time. Now, let's compare the parent function to another function that has some up, down, left, right stretching and shrinking going on. So the first thing I want to identify is there an a value? Is there a value other than 1 in the numerator? And the answer is yes. A equals 3. So my a value is 3. Well, it's positive, so there's no reflection, and it's bigger than 1, so that means it's going to be a vertical stretch by a factor of 3. And that's how we want you to answer it, vertical stretch by a factor of 3. Now let's see, is there an h value? Well, x minus h, x minus 2, so h is 2. So that means my graph is going to go to the right 2. Well, if my graph goes to the right 2, my vertical asymptote also moves right 2. Now let's see, is there a k value? There is. K equals 1. So k equals 1 tells me that my graph is going to move up 1. But if my graph moves up 1, so does my horizontal asymptote. It also moves up 1. So let's talk about the equations of the asymptote. So the vertical asymptote is x equals h. Well, I know h is 2, so that's x equals 2. The horizontal asymptote, we remember from the last slide that it is y equals k. Well, my k value is 1, so that's y equals 1. Okay, now let's talk about how we graph this. There's a step-by-step process. The first thing you want to do is you want to plot your asymptotes. Well, we found out on the last slide that I have one asymptote at x equals 2, and I have the horizontal asymptote at y equals 1. So that's the first thing we're going to do, is we are going to plot those asymptotes. Step 2 is you're going to make your parent function table. Well, if you remember, it was -2 to 2, and then -0.5, -1, undefined, 1, and 0.5. There's my parent function. Now, we are going to manipulate the table using A, H, and K. So to go from old x's to new x's, it says I subtract 2, but remember, it's opposite day. It's opposite day. So instead of subtracting 2 from every x, I'm going to add 2. Now, for the y value, A and K affect the y value. So do I multiply by 3 and then add 1, or add 1 then multiply by 3? Remember, PEMDAS is still in effect, so we have to multiply by 3 and then add 1. So let's do the x's first. So -2 plus 2 is 0. -1 plus 2 is 1. 0 plus 2 is 2. 1 plus 2 is 3. 2 plus 2 is 4. And now let's look at the y's. So for the y's, we're going to multiply by 3 and then add 1. So 3 times -0.5 is -1.5 plus 1. So it's still -0.5. 3 times -1 is -3. -3 plus 1 is -2. Now you can't do anything to undefined, so he just comes along for the ride. So now we go to 1. 1 times 3 is 3. 3 plus 1 is 4. And then 3 times 0.5 is 1.5. 1.5 plus 1 is 2.5. So now we're going to plot and connect the dots. So I plot my points and I connect my dots. And notice that after I connect, they're going to hug those asymptotes. They're never going to cross them, but they're going to get super duper as close as they can. All right. Now let's talk about domain. Remember, you can do it one of two ways. Domain is negative infinity to h union h to infinity, or negative infinity to the vertical asymptote union vertical asymptote to infinity. So either way, my h is 2. So I'm going to go from negative infinity to 2 to infinity. All right, and then let's talk about those horizontal asymptote and the range. So if you remember, the range is negative infinity to k, k to infinity, or negative infinity to the horizontal asymptote to positive infinity. So negative infinity to 1, union 1 to infinity. And that's how we come up with our range. Okay, on this slide, they want us to write an equation for the transformation of the parent function, f of x equals 1 over x, given f of x equals a over b times x minus h plus k. So in the first example, they tell me that a is negative 2, h is 3, k is negative 4. They didn't give me anything for the b value, so I just don't worry about him. And so all I'm going to do for this example is substitute negative 2 for a, 3 for h, and negative 4 for k. Ta-da! Just that easy. Let's look at another example. Here they tell me that the horizontal asymptote is at negative 2 and the vertical asymptote is at 5. Well, I remember back from that slide that the horizontal asymptote is y equals k and the vertical asymptote is x equals h. So that tells me that k is negative 2 and that h is 5. It didn't tell me anything about a, so since it didn't tell me anything about a, I'm going to leave a 1. So my new equation is y equals 1 over x minus 5 minus 2. Now let's talk about the domain and the range in interval notation. Well, the domain, if you recall, is negative infinity to h, h to infinity. So my h is 3. So negative infinity to 3, union 3 to infinity. Again, we can't touch 3 because my asymptote is at x equals 3. So I'm never going to touch it. That's why it's parentheses. Now my range is negative infinity to k, union k to infinity. So it's going to be negative infinity to negative 4, union negative 4 to infinity. Now, for the second example, my h is 5. So my domain would be negative infinity to 5, union 5 to infinity. And my range is the k. So it's negative infinity to k, which is negative 2, union negative 2 to infinity. And then lastly, if you want to write it or you're asked to write it in set notation, you basically say, for domain, the set of all x's such that x is not equal to h, because it's undefined there. So it'd be x such that x doesn't equal 3. For range, it would be the set of all y's such that y doesn't equal negative 4, because that's where the asymptote is at. Same for the second example. Our graph cannot exist at 5, so we would say the set of all x's such that x doesn't equal 5. Same for the range, the set of all y's such that y doesn't equal k, which in this case is negative 2. Okay, let's look at our last example. The rowing club is running a 57-passenger bus for a day trip. The cost of the bus is $750. 5 passengers will be chaperones. So the first question says, if the students who attend share the bus cost equally, what function models the cost per student C with respect to the number of students who attend? Okay, so basically, if I wanted the cost per student, I would just take the cost of the bus, $750, and divide it by the number of students in. So $750 divided by the number of students will tell you your cost per student. So the second part, the cost per student depends on the number of students attending. So what is the domain of the function? Well, I know that the bus holds 57 passengers. 5 of them are going to be chaperones. So we're not going to make the chaperones pay. So if it holds 57 and 5 of them are chaperones, that means I can have a maximum of 52 students. So the domain, now you could say the domain is 0, but if 0 students are going to attend, there's no point in taking the field trip. Okay, so your domain is going to be integers between 1 and 52. Now, let's talk about why it has to be integers. Okay, you cannot take half a person. You cannot say, I'm sorry, only your arms and torso can go. You can't do that. You can't take a part of a person. You have to take the whole person. Okay, so since you can't take just part of a person, you have to take the whole person. So that's why we said integers. So we can't take 5.5 people because we're like, I'm sorry, only your arms can go or whatever. Okay, so you have to take a whole person. So that's why we use integers. Okay, so now last question. It says, how many students must ride the bus to make the cost per student no more than $20? So $20 is as much as the cost can be. So we sub in 20 for the cost. Now, the cost must be less than or equal to $20. So we used an inequality in this because we don't want the cost to be any more than $20. But we solve it just like it's an equal sign. So, little cross multiplication, because you put 20 over 1. And so we get 20n equals 750. We divide by 20 and we get 37.5. Okay, again, we can't take half a person. We can't be like, Jim Bob, I'm sorry, only part of you can go. It doesn't work that way, okay? So we have to take 38 people. Now, you might be asking, well, why couldn't I just take 37? Because if you do 750 divided by 37, your cost is more than $20 per person. So that's why we have to round it to be 38. We need that 38 student to go to make our cost less than or equal to $20 per person. All right, and that's it. That's all you have to do. All right, so you may now go and begin your homework 6.2. All right, have a good afternoon. Have a good day. We will talk to you next time. Bye, everybody. Oh, and please, please, please social distance. Wash your hands. Wear your mask. Stay 6 feet apart because we want to have you guys healthy and safe. That way we can all get back to what we are going to consider our new normal. All right, have a great one, and we will talk to you soon. Bye-bye.